We left off last time talking about hydrogenation, catalytic hydrogenation. So here's the story here. We use hydrogen gas and a catalyst. So there's many catalysts. I'm only going to talk about palladium, platinum, and nickel. And what I typically use is palladium, just to make it easier for you, less for you to memorize. So I usually use palladium. Highly exothermic reaction, but it has an enormous energy of activation. So you need a catalyst. It doesn't really happen without the catalyst. All right, so typical catalysts, I didn't leave myself enough room. So palladium, platinum, and nickel. And of course, I'm going to be using the palladium. So that's the one I'm going to use. So the catalyst changes the nature of the transition state. I don't want to suggest that this is the actual energy diagram for the catalytic hydrogenation. The point I'm trying to make with this energy diagram is that when you add a catalyst, you change the reaction pathway. And it doesn't have to be the same pathway, so it's not a one-step process by any means. It's just that you provide a different pathway that has lower energy. So as you can see that this would be way too high of an energy of activation for the uncatalyzed reaction, never happens. Okay, so EA is huge. So reaction doesn't go. Without catalyst. So in other words, you can't assume just because this is a very exothermic reaction that your reaction is going to go easily. If it has a very high energy of activation, then it's not going to go easily. So here is the catalyzed reaction. And again, this is just generic. But you can see that this is a much smaller energy of activation. Then we still have to come up with this much more. But even so, much lower energy of activation. So this whole thing is the catalyzed reaction. So in this case, the catalyst provides a different lower energy pathway. All right, so that's all we need to know about that energy diagram. Here's an example of a catalytic hydrogenation. We take a polyunsaturated fatty acid, H2 nickel. So you will recognize this from the podcast. This is a 1, 2, 3, 4, 5, 6. This is a polyunsaturated omega-6 fatty acid. And so this has a melting point of -8 degrees centigrade, so liquid at room temperature. And then once we hydrogenate that, we get a saturated fatty acid. Solid at room temperature. All right, so this would be fully hydrogenated fatty acid, and then of course we have partially hydrogenated, and when we partially hydrogenate, we use a different catalyst. We still use H2, but we use a different catalyst, and in that process some of the cis double bonds become trans, and that's when it becomes really harmful to us when we do that. So that's the whole idea. This is a fully hydrogenated. So how does this work? I don't want you to think this is a mechanism. You don't have to draw these guys on your test. I'm not going to ask you any mechanisms from this chapter, but I want to give you an idea, a little bit of an idea of how this happens. And so just going to go take you through the process. Hydrogen is AD, adsorbed. Not the same thing as absorbed. It's AD, adsorbed onto the surface of the metal. And when it does that, we're going to get these hydrogen, the hydrogen bond breaks apart, and we're going to get a bunch of these guys here on the surface of the metal. So that's the hydrogen adsorbed. And then what happens is we've got this hydrogen adsorbed. Let's continue with these guys here. The alkene moves in. I'm going to tilt this alkene on its side. So let me just wedge that, or dash that. No, that doesn't look dashed, does it? Let's erase that and start over again here. So I'm going to turn this alkene on its side. This is going to approach the surface of the metal. It's going to get closer than that, but I can't get too much closer because I have hydrogens in the way, as you can see. That's going to come close to the surface of the metal. And when it comes in the vicinity of one of these, let's add some new hydrogen here. These are going to add to the same side here. So what's going to happen in this next phase is that we've got our hydrogens here. The alkene goes away, and now we have something that looks like this. This is now bonded to the surface of the metal. We've broken the pi bond. Again, you're not going to have to reproduce this. And then what happens is that one of these hydrogens like these guys here, which I didn't have room for, are going to add to the same side. And so what you get is something that looks like this. You have these hydrogens going back, this hydrogen coming forward. And then it's released. Once this hydrogen adds to the same side, I'm not going to really do arrow pushing here, but you can see that, and we still have these other hydrogens here ready to add to another alkene when it bonds to the metal. And then that goes away, and so this is the H2 added to the alkene. So it is a syn addition. Very important that you know that, syn addition. So the overall result for this reaction here is syn addition of H2 to the alkene. There is an addition summary page that I forgot to add to the practice link. I'm going to add that this afternoon, and that summarizes all the addition reactions we talked about, and I actually have this one on there also. So there's syn addition, there's anti-addition, and then there's reactions that give a mixture of syn and anti. That handout will really help you when you're trying to kind of get all this stuff together from chapter 10. All right, questions so far? Anybody? Let's talk about hydrogenation of other double bonds. So ketones and aldehydes can be reduced with H2 and nickel, palladium, or platinum, although it is much more common to use lithium aluminum hydride or sodium borohydride for the same reduction. So we're not going to use this very often. More common. This is chapter 20. which is one of the first chapters we talk about in 51C. So right now, this is our only way to reduce double bonds. But lithium aluminum hydride and sodium borohydride are going to be really important reagents in 51C, and it's a more common way to do this. But notice here, this is ketones and aldehydes, not carboxylic acids, esters, amides. Okay, just ketones and aldehydes, not carboxylic acids, esters, and amides. And we can prove that because we just did it right at the top here, didn't we? Let's go back here. When we hydrogenated this polyunsaturated omega-6 fatty acid, we reduced the alkenes. We did not touch the carboxylic acid, right? This will not work for carboxylic acids, so that makes a good point there. All right, so let's see what that looks like. Same idea here. We're adding hydrogen. I'm just going to drop this as it comes in. We're adding the elements of hydrogen to that carbon-oxygen double bond. So when you do catalytic hydrogenation, here's what you get. So H2 added across the double bond. It's a syn addition. So it's okay to use that now, but when we get into chapter 20, you're going to use lithium aluminum hydride or sodium borohydride and a BH4 instead in 51C. So this is going to make more sense to you when you come back and look at these notes when you're already in 51C. Carbonyl groups of esters, amides, and carboxylic acids are resistant to hydrogenation and will not typically react with H2 palladium, platinum, or nickel. And so as you can see here, this is a no reaction. All right, and that leads us right to, is page 90 correct? Yes, page 90 is correct. That leads us to reduction of alkynes. So what happens if we reduce an alkyne? Now we have an alkyne, we have 2 pi bonds. And it turns out we can reduce one of them or we can reduce both of them. We can do either. So if we do full hydrogenation, I'm going to draw the carbon skeleton and then I'm going to draw the hydrogens that come in a different color. So you can see what's happening here. We're going to add it twice. So here's one of the pi bonds being hydrogenated, and then we can hydrogenate the second bond. And if we use these catalysts here, we will get full hydrogenation. Even if you use one equivalent of H2, you will still get full hydrogenation. Why? The catalyst is too powerful. And good luck trying to only use one equivalent of H2. It's a gas, right? So how are you going to do that? How are you going to measure out one equivalent of H2? It's really not. It's doable, but it's not easily doable. So if we want to just add hydrogen once, we have to use a different catalyst. So the way that these catalytic hydrogenations are done, they're kind of fun. You've got your stuff in a round bottom flask stirring in a solvent, and then you fill up a balloon with hydrogen gas. You put a little needle on the end and you stick it in there. So, and that's how you do it. So really difficult if you only needed one equivalent of H2. That's going to be very hard to do. So if we want to do partial hydrogenation, we have to make the catalyst less powerful, and that's the way we're going to do it, rather than trying to limit the H2. So the way we make the catalyst less powerful is we use poisoned catalyst. It's called poisoned catalyst. And what you do with Linlar's catalyst, and I'll show you what that is on the next page, what happens with Linlar's catalyst, the poison catalyst, there's reagents that are added to it that tone down the reactivity, and poison's kind of a good word there because, and that's what it seems like it's doing. Making it less reactive because it's poisoning the catalyst. So this is what it would look like. Syn addition, right? So let's draw the hydrogens in a different color so you can see. Syn addition, those are the new hydrogens that you've added. So Linlar's catalyst. So this is stereoselective syn addition to give the cis alkene. Need to know that. Stereoselective syn addition to give cis alkene. If you want trans, sometimes you want a trans alkene rather than a cis. We're going to use a different reagent, and this is called a dissolving metal reduction. So you take a chunk of sodium, you add it to liquid ammonia. Ammonia is a gas at room temperature. You cool it down to -78. You add a chunk of sodium, and then you add your alkyne, and you will get stereoselective anti-addition. So let's draw that again. Our skeleton here, and as you can see, now we're going to get trans. I will not show you the mechanism for that. It's a little complicated. It involves radicals. And we don't talk about radicals until chapter 15. So it's not really something that's appropriate to show you right now, and I'm not going to show you even after we do chapter 15. All right, so this is stereoselective. Anti-addition. To give the cis alkene, or the trans alkene, yeah. Questions about reduction so far? Okay, so how do we poison palladium catalyst? We add lead and quinoline, and that reduces the reactivity. So here's Linlar's catalyst. Don't try to find this in your book. They don't show you. And here's the way it works with me. You can just write Linlar's catalyst. You don't need to draw out what all the reagents are. This is palladium on calcium carbonate. So what does that mean? Since this reaction takes place on the surface of a metal, if you increase the surface area, you increase the rate of the reaction. So very often the palladium is deposited on something that has a lot of pores so that you can increase the surface area. And so that's with the palladium on calcium carbonate. And then you add lead acetate. So lead poisonous for us, also poisonous for the catalyst. We won't go into the details of why that is, but it is the case. And quinoline. All right, so that's Linlar's catalyst, and like I said, you can just write Linlar's catalyst, but what some people do is they'll write Linlar's catalyst, but they'll forget the ever important H2. You have to have a source of hydrogen to add to the alkene, so you need to, don't forget to add the hydrogen. NH3 liquid dissolving metal reduction ammonia, which is a gas, as we talked about this. We take a chunk of sodium. The sodium becomes Na plus when it donates an electron, and the NH3 becomes NH2 minus when it loses a proton. So this was that second type of reduction that we were talking about. So NH3 liquid is a source of 2 2 electrons plus 2 hydrogens, 2 protons, 2 electrons and 2 protons. All right, the third type of reducing agent that we're going to talk about is lithium aluminum hydride. And that is, it's a hydride reagent. The reaction follows an SN2 mechanism. Here's what it looks like. The lithium, we're going to assume is a spectator ion, so you can completely leave that out entirely. Here's what aluminum hydride looks like. AlH4. There is a negative charge on aluminum. And it is a hydride source. So we're going to be transferring one of those hydrogens from aluminum, and we're going to be using that to attack the carbon. So let me put lone pairs on the bromine. We're going to actually do an SN2 reaction here. Let me change the color so it's a little clearer. The arrow can come from any one of the aluminum hydrogen bonds. We're going to attack carbon, and we're going to break the carbon-bromine bond. And so we've replaced the bromine. So this is a substitution reaction where hydride is our nucleophile. And this is a very, very powerful, lithium aluminum hydride is a very, very powerful nucleophile. It's also a powerful base. Powerful base, base/nucleophile. And we know it's a very powerful, we know it's a very powerful nucleophile because it does, this reaction is a very fast reaction. We know it's a very powerful base. We look at the pKa of the conjugate acid. The conjugate acid is H2 if it acts as a base, and that is approximately 35. And so we know it's also a very powerful base. So it can do the same things that some of our other good nucleophiles do. It can also open up an epoxide. So this is what it would look like if it opens up an epoxide. Here's our reagent. This is what I like to call famous reagent, meaning that you will use it a lot. This is going to be really, we're not using it that much right now, but when you get into 51C, you will use it a lot. And so it's a really important reagent to tuck away and think about using in a synthesis. So what it would look like here, again, the arrow comes from the aluminum hydrogen bond. It's a powerful nucleophile, so we attack on the least substituted side. Oh, what happened to my first arrow there? How about that? So attacks at least substituted side. And once you do that, you open up the epoxide. O minus. So this looks like something straight out of chapter 9, the last part of chapter 9, and it's really, this is going to react just like the strong nucleophiles in chapter 9. HOH, you can also use H3O plus here, and really we're adding a second acid step because we want to protonate the epoxide. And so that's all we're doing in that second step. All right, so extremely powerful nucleophile. Make sure that you number these steps. So number steps. Really important. And the reason is if you add lithium aluminum hydride to water, it's going to blow up right all over you, okay? It's very, very powerful. When you do this reaction, you do the lithium aluminum hydride, you let the first reactant run its course. Once we get everything converted into this, you plop that reaction vessel into an ice bath. You let it cool till it's very, very cold. You cautiously add a drop of water, and you'll see hydrogen gas coming out, a very violent reaction. You wait till that cools off, stops, and then you add another drop cautiously. So I am really particular about this numbering here. If you mix these together, you will not get any reaction, you won't get any points. So make sure that this is lithium aluminum hydride and this is water. I had an explosion in grad school with lithium aluminum hydride, so I have a tremendous amount of respect for this very powerful reagent. I was actually doing a distillation, and the lithium aluminum hydride was used as a drying agent to get rid of water in my reactant that I was trying to do. And so I had it going in my hood, and I lowered the lab jack, and I saw I still had some more left in there. I raised the lab jack, closed the sash, and went boom, boom, and the whole thing exploded. So I was like seconds away from getting my hand blown off, honestly. So maybe I am particular about the numbering of these steps, but I have good reason to be, right? Gosh. Anyway, so it's very powerful, it's that powerful, and so certainly we want to do this cautiously. We want step one, and then we add the water and the hydronium ion in a second step. All right, so lithium aluminum hydride is a source of the strongly basic hydride ion. Since this is an SN2 reaction using a strong base, it works well only for unhindered primary and methyl substrates. And of course, we can also attack epoxides. And I wanted to try this when it's doing this weird scrolling thing. No, it's not going to let me do that. Okay. And so because it's a strong nucleophile, it attacks at the least substituted side. I do want to make a point here, and that is that NaH will not work for this reaction. So don't try to use any, you might think to yourself, I'm really clever. I know sodium hydride, and that's easier to remember. H minus is easier to remember than AlH4 minus. I'm going to use that instead. Sodium hydride does not do the same reaction that lithium aluminum hydride does. Even though they're both hydride sources, the difference here is that sodium hydride is actually, this is an H minus, this is actually an ionic compound. This is a covalent bond here between the aluminum and hydrogen. And so they don't react the same way. NaH only does acids and base reactions. It never acts as a nucleophile. So that's a good thing to remember. Let's write that down. NaH only does acid-base reactions. It never acts as a nucleophile. To do substitution reactions. You could actually categorize an acid-base reaction as it's acting as a nucleophile, but it doesn't. It only does Bronsted. Let's clarify that. Bronsted acid-base reactions. It never acts as a nucleophile to do substitution. Substitution reactions. Okay, so something to keep in mind about sodium hydride. Questions so far? Anybody? That's it for reduction reactions. Now we're going to talk about oxidation reactions. And look at all these reagents that we got to kind of get straight. I'm going to circle the ones that I use most, so that will limit the amount that you have to memorize. So we had 3 different types of reagents for reduction. Now we're only going to have 2 different types. Number 1 is reagents that contain an oxygen-oxygen bond. So we've got O2, ozone, hydrogen peroxide, tert-butyl hydroperoxide, peroxy acid. What are we going to use? That's a peroxy acid, isn't it? These guys are the ones we're going to use. This is a peroxy acid. So peroxy acids are the things that we're going to use. Benzoyl peroxide is a peroxy acid. And yes, that's the same stuff that you get in acne medicine. Benzoyl peroxide, you're actually putting it on your skin. That's one of the reagents in this category. And then reagents that contain a metal-oxygen bond would be the second type, chromium reagents. So we have this. I will be using this. This is another form of that. Na2, sodium dichromate, is interchangeable. This is the one I use. I use this one. I also use this one. PCC is one of those famous reagents that you're going to use a lot. So this is an important one. I also use this one. KMNO4, sodium hydroxide, we will also use that one too. Osmium tetroxide, silver oxide don't really use. There is an osmium tetroxide reaction that I will also use. But not as much. The famous ones are these guys that I use a lot. The chromium reagents here, both of the chromium reagents, and these guys not as much, but they also do some unique reactivities that we have to talk about. Questions? Did somebody have? Okay. We're going to talk first about epoxidation. And epoxidation, that's when we're going to use the peroxy acids. So epoxidation is the addition of a single oxygen to an alkene to form an epoxide. Famous reagents. You're going to use this a lot. And so here's the idea. We have an alkene plus a peroxy acid. I'll show you stereochemistry in a minute. This is what I'm just drawing this without stereochemistry. Your side product is a carboxylic acid. The mechanism is not on the test, but I'll show you because some people like the mechanism. They like to see it. It makes more sense if they see it. So here's what the mechanism looks like. Here's our alkene. And just in case you don't remember when you come back to this, let's just write that. Mechanism not on test. Again, I told you I wasn't going to ask you any mechanisms from chapter 12. So this is chapter 12. I'm not going to ask you that. And you'll see why I don't ask you this. It's very strange looking arrow pushing. I remember having to memorize this mechanism when I was a student, and it didn't really help me with anything. It was a little crazy and a little hard to wrap my head around. And once you see that, I will definitely change colors here. So once you see the arrow pushing, you'll see why. So first arrow comes from the pi bond to the oxygen. And then we break the oxygen-oxygen bond. We move this over. This arrow comes and picks up this hydrogen. And the electrons from this bond come in and attack the other side. Aren't you glad you don't have to remember that? So basically, think about it this way. We have the peroxide, and we're delivering one of the oxygens to the alkene to make an epoxide. And I am going to show stereochemistry here. And the reason I'm showing stereochemistry here is because we have stereochemistry about the alkene. We see that we start with a cis alkene. If we start with a cis alkene, we will get the cis epoxide. And your side product, which we're going to not worry about, but I'm going to draw it here just to complete this, is a carboxylic acid. Do not need to include that if I have a predicting products. This is a carboxylic acid side product. On the test, you only would have to draw this if it's a predicting the products. All right, the most common peroxy acid is metachloroperoxybenzoic acid, and this is the only one that I will use. What I like about this one, it's the most common one, and it has a nice little abbreviation, a little MCPBA. Can use abbreviation. But please be aware that that's a peroxy acid, because I think there's some problems in Sapling and probably in Smith where they use just a peroxy acid that's not specifically MCPBA, and you'll be thrown off if you don't realize what that actually is. All right, so here's an example here. This is the only peroxy acid I will use. So here's an example. We start off with E2-butene, also known as trans-2-butene. And that is an achiral reagent. So we're going to keep track of this, achiral. We do have stereochemistry about the alkene. It is trans, so we want to notice that. MCPBA is also achiral. So if we react achiral reagents, so we have no chiral influence and we're making a new stereocenter, then we must get a racemic mixture. We must get a racemic mixture. So we're going to get a pair of enantiomers. So let me draw the two enantiomers. How do we get a pair of enantiomers? Oxygen can come in from the top or the bottom here. But do notice the methyls, the relationship between the methyls. They are trans in the alkene, and they are trans in the epoxide also. That's important. To get the other enantiomer, because remember, this alkene is planar, so the peroxide came in from the top or it can come in from the bottom. To get the other enantiomer, the oxygen comes in from the bottom. So it looks like that. Let me move this plus sign over. Those are the two products. So a pair of enantiomers. Reaction stereoselective. E2-butene gives only trans 2,3-dimethyloxyrane, and Z gives only cis. So we maintain the stereochemistry of these two methyl groups in the alkene. This actually gives the same, exactly the same product that we get with our other way of making epoxides. Our other way of making epoxides is to make a bromohydrin and then use sodium hydride. Okay, so that's the other way. We get the same exact product mixture. Plus an enantiomer. So it's the same two enantiomers you get. So these reactions are interchangeable, but I will tell you right now that everybody likes using MCPBA rather than using two steps. So you can use these interchangeably. Probably from here on out, no one's going to use this second method. Everyone's going to use MCPBA instead, and that's perfectly fine. All right, so as you can see, we have, because of the fact that we have this is achiral, and this is achiral, we're going to get a pair of enantiomers. What if we did have some kind of chiral reagent here, and we could just get one epoxide and not the other, a single enantiomer? And that's what happens in the Sharpless asymmetric epoxidation. He actually makes a chiral catalyst. The reagents are shown on the next page. This is a titanium catalyst. And you use one of the two of these, the plus RR tartaric acid or the minus SS tartaric acid. And that, the one that you choose depends on which enantiomer you're trying to make. And then all of these two reagents are in catalytic amounts. And what happens is that these reagents assemble themselves into a chiral catalyst that, the way to think about it is it's kind of going to act like an enzyme. Because it's chiral, it's going to react to give only one of the products. This is terp-butyl hydroperoxide. This is one equivalent. So these are catalysts, and then we only have one equivalent of that. And so instead of getting a racemic mixture, you can get a single enantiomer. So here we have achiral. This is achiral. But this is chiral. And you can see that you can choose which enantiomer you want based on the catalyst that you use. Now, there's reactions in your Smith book where they have you predict the correct enantiomer. I'm not having you do that. Okay? So I don't want you to do that. I'm not going to ask you to predict the correct enantiomer on the test. I'm trying to show you an idea rather than having you predict. Okay? So very highly enantioselective. You can change the stereochemistry. This reaction plus some other work that Sharpless did actually earned him the Nobel Prize. So it's a really important idea and concept that's super important to think about, especially if you're a chemistry major. All right, the reaction only works with allylic alcohols, so we know what an allylic alcohol is. So if you do the reaction with just with this compound here, the only alkene that you're going to put an epoxide on is one right here, and that's because this OH also attacks the titanium and is part of the catalyst. Okay, so this will be left alone. This only works with allylic alcohols, and so this is the product that you would get. Again, don't think that you need to predict these products on the test. That's not important, and I'm not going to ask you that. And so, but students usually think that I'm going to ask this question on the test because Professor Sharpless was a professor when I was in grad school, and I actually TA'd his class 2 times. And so when I got my Ph.D., I have a picture of me sitting with Dr. Sharpless, and he's holding one of my molecules that I made. And so it's this nice picture with a Nobel laureate. But that doesn't mean I'm going to ask you to learn this just because I like, I like the reaction and I like the work he's done. I always ask you questions that are going to be important for you moving on in the series, and this is not important for you moving on in the series. So it's just more about a concept here. All right, questions? Anybody? All right. Dihydroxylation is the next reaction. Yes? You certainly can. Yeah, you certainly can. All right. But you don't need to pick the correct catalyst. You won't, because you don't need to remember that. All right? There is a mnemonic for drawing the correct product. I do not want you filling brain space with that mnemonic. Okay? So that's not important for you to move on in the series. So, dihydroxylation, vicinal diols. So that means we get 2 alcohols right next to each other. And there's 2 reagents for this. This is the one that I use. And the only reason I use that one is because you've seen potassium permanganate before, haven't you? You remember that from Chem? KMNO4? Purple. Did you use it in the lab? Yeah, purple, right? And then when it reacts, what happens? Do you remember? I have such a vivid image of this. brown sludge on the bottom, right? MnO2 is brown precipitate, ugly. So you start off with this beautiful purple and then you get brown precipitate. So the reason I'm using that is because it's already familiar to you a little bit, I hope. And so that's the one I ask. So it's a syn dihydroxylation. So that means that the two hydroxyls come in on the same side. What? Did I skip? Oh, hydrogens. What am I doing here? Yes, I am skipping. I am skipping ahead here. Thank you for pointing that out. Right? So syn addition of two hydroxyls to an alkene. So now we've got colors here. Let's label this as purple with a purple pen. How about that? I don't have brown. I probably have brown somewhere here. That's brown. Let's do this. Plus a brown MnO2. It's not really quite brown, but it's close enough. And I'll put a little arrow because it's a precipitate. So brown precipitate. Just so you have a visual there, okay? So in addition to two hydroxyls, you can also do the same thing with osmium tetroxide. Also a syn. Oh, now we're in the color brown here. Okay, that's cool. Here's my methyl on one side. Here's my hydrogen on the other. And then I've got my OHs. Also syn dihydroxylation. Will we get an enantiomer here? Yeah, it's acarbonyl. Acarbonyl, we're making 2 new stereocenters plus an enantiomer. Did I leave off plus an enantiomer on this previous one? Is that chiral? No. Careful with that plus E that you're going to be allowed to use on midterm 2. That is achiral, so we won't have plus E. There's a plane of symmetry here. This one is not achiral, so we have to have, we will definitely have the enantiomer. This is also a syn dihydroxylation. I believe that these two reactions are also on the addition summary sheet that I'm going to be posting this afternoon. If not, then you can print it out and add these to it. All right, so here's an example. Here's an example here. How do we make, so these are 2 ways to do syn. How do we do trans dihydroxylation? Opening up an epoxide, right? So you make the epoxide, MCPBA chloroform, or step 1, bromine water. Step 2, NaH, right? Those are interchangeable. We make an epoxide. So this is old news. We already know this. And then we can do sodium hydroxide water, or we can open this up with acid, or H3O plus and water. All right, if we use sodium hydroxide, hydroxide attacks. And then we break this carbon-oxygen bond. That gives us this. This is going to be here, O minus. We have our hydroxyl coming up here. And then we protonate. Here we would protonate with water. So definitely, can you see that that's a trans dihydroxylation? So our product is trans. So need to know that. To do cis, we're going to do potassium permanganate. And to do trans, we're going to do epoxide and then open it up with either acid or base. That's a perfect stopping point. We'll stop right there. I hope you guys have a great 3-day weekend.